Hello, this is question 6 from the 2019 MAT. A flexadecimal number consists of a sequence of digits with the rule that the rightmost digit must be 0 or 1, the digit to the left of it is 0, 1 or 2, the third digit, counting from the right, must be at most 3, and so on. As usual, we may omit leading digits if they are 0. We write flexadecimal numbers in angle brackets to distinguish them from ordinary decimal numbers. Thus, 34101 is a flexadecimal number, but 231 is not because the digit 3 is too big for its place. Oh yeah, that one can only go up to 2. If flexadecimal numbers get very long, we will need digits, in inverted commas, with a value of more than 9. Well, same in hexadecimal. The number 1 is represented by 1 in angle brackets in flexadecimal. To add 1 to a flexadecimal number, work from right to left. The rightmost digit is a 0, replace it. It's just telling us how to write down numbers, right? This is just, well, we do this in decimal, we just don't think about it. And if you've done binary before in any way, then you're probably familiar with this, of how to write out binary numbers. Thus, when numbers 1 to 4 are represented, right, okay, 1, 10, 11, 20, okay, yeah, write down the numbers from 5 to 13 in flexadecimal. So 4's got us up to 20. So 5, 6, 7, 8, 9, 10, 11, 12, 13. So that would be adding 1 on. Then when we go to 6, well, we can't go higher than 1 on the right hand side. So we start at the right, we can't go higher, so we drop it to 0. We take that 1 to the next column, but we can't go higher than that, so we drop it to 0. We then take it to the next column and put a 1 in. So that's our 6. And we just keep doing the same process. That way we can add 1 to the end. Now we can't. Now we can. Now we can't at the end, so we get 120. Then we're going to get 121. Now the 2 right-hand columns are filled up, so we're going to have to go to 200. And then we'll have a 201. So that was just standard writing out the numbers in a different, well, this is a weird sort of base, but there you go. Describe a workable procedure for converting flexadecimal numbers to decimal and explain why it works. Okay, well, this is going to be similar to how we convert binary then. You want to look at the column. So you want to have some value that a number in a column is worth. Well, it's the same that we have in decimal as well. So how much is each column worth? And then how much have we got in each column? So we need to go through each one and work out, well, first of all, what are these columns worth? So let's see if we can get a pattern then. So say we've got some flexadecimal number that's like A, B, C, D going off forever, going from right to left. How much is a digit in each column worth? So in the rightmost column, we know they're just worth 1. In the next one, in our B column there, they're going to be worth 2. And we can see this in our 5 here. So we've got 2 2s and a 1 makes 5. So the next one must be 6, because that's how we're getting 6 from 1, 0, 0. So what are we going to get from the next one along then? How many 6s? We can have 3 6s. So we'll be able to get 18 plus 5, 23 out of the ABC. So D must be worth 24. Right, now we're getting our pattern, because these are factorials. So 1 factorial, 2 factorial, 3 factorial, 4 factorial. So we want to set up our column numbers. So that's step number 1 then. So we're going to say label columns from left, from right to left. We have to go right to left with numbers 1, 2, 3, etc. So we have that, and this will be, we can call this the column number C. Let's call it that. Then we want to say for each column we want to take digit, well, let's call that D, and calculate. So we want to do the digit multiplied by the factorial of the column number. Then add up all these numbers. So we have to then demonstrate this on 1, 2, 2, 1. So e.g. 1, 2, 2, 1 is going to be equal to 1 times 1 factorial plus 2 times 2 factorial plus 2 times 3 factorial plus 1 times 4 factorial. So that is 1 plus 4 plus 12 plus 24, which when we put it all together is 41. Right, that certainly filled things up. So new sheet. Right, part 3. Describe a workable procedure for converting decimal numbers to flexadecimal and demonstrate it by converting 255 to flexadecimal. Right, well, this is the same as we do for other bases. We take the largest factorials at a time. We chunk these off and fill up the columns as we go. So 255 is what we're going to be doing with. So we take largest possible factorial away and add a 1 to the appropriate column. So in this case, we're going to, and then repeat. So in this case, then we're going to be taking off 120. So so we start off 255 is equal to 120 plus 135, which is 120, plus 120 plus 15. So that's 120 plus 120 plus 6 plus 6 plus 2 plus 1. So let's split that out. Now we just have to put all of those into the appropriate columns and then we're sorted. So 255 is going to be equal to, so 120 is our fifth column, we've got 2 of them. Then we've got no 24s. Then we've got 2 6s, 1 2 and 1 1. So 2 0 2 1 1. Okay, so that's done part 3. Then we've got part 4. We could add flexadecimal numbers by converting them to decimal, adding the decimal numbers and converting the result back again. Describe instead a procedure for addition that works directly on the digits of 2 flexadecimal numbers. Demonstrate it by performing the addition 1 2 2 1 plus 2 0 1. Right, this is going to be similar to normal addition because we've got this weird way of, we can go, the number of digits we got in each column. So, right, let's think through or maybe I'll demonstrate it and then say what the procedure is afterwards. Maybe that's going to be a better way of doing it. So we're doing 1 2 2 1 and then we're adding 2 0 1. So we've got those 2 1s at the end make a 2. So we are going to put that to be a 0 and then carry 1 2 over is what we're taking across. Now we've got 2 2s and a 1. So that's making 6. So that's going to be a 0 again and we're carrying a 6 over. We've now got 5 6s. So if we've got 5 6s, we only need to carry 1 of those over and we're going to have a 6 left. And then we got a 2. Right, so that's what we want to end up getting. Thing is, how do we describe how much we're carrying over? So in this case, we had so for the first column, we had a 2. So we went down to 0 and we carried 1. In the next one, we had a 3 and we went down to 0 and carried 1. And then in the next column, we had, what did we have here? We got 5, haven't we? And we've carried over 1, we've left 1 and carried over 1. So we got a difference there. How much are we actually removing here on each time? We can only go but we only need to take off one more than the maximum of the column, because then we don't have enough to carry over. So we're taking, so for some columns C, so what are we doing here? We're adding them up. So we add, so for each digit, for each column, starting on the right, so we want to add digits. Then we're going to want to take off the column number plus 1, aren't we? That's what we're going to want to do if it's gone above the column number. So if the add digits, if the sum is less than or equal to the column number, then move to column on the left. Else we've got the sum, not that we really have to put it in, but the sum is greater than the column number. Then we need to subtract the column number plus 1 and carry 1 to the left hand column, and then continue. So it is much the same as what we do with regular adding up, whether it's in decimal, binary, or whatever we're doing. We've just got that twist of the amount that we're removing depends upon the column number. It's not just a fixed amount in each column. It's not just it's not a fixed amount in any of them, but in terms of like in binary, you can only have zeros or 1 in every one. In decimal, you can only go up to, you've got 0 to 9 in each one, whereas here we got a different number of digits you can have in each one. So we got a different amount that we have to subtract when we're carrying over from one column to the next, depending on which column we're in. So that's the fiddly bit about dealing with these flexadecimal numbers. But the process is so similar to just adding in decimal or binary or any other base that it's quite easy to pick out the pattern if you're familiar with working in those bases. Right, third sheet onto now. Given a flexadecimal number, how could you test whether it's a multiple of 3 without converting it to a decimal? How can we test if it's a multiple of 3? Right. This would be interesting. So we've got some number, which is, so what were all the columns worth? So we've got 1 factorial, 2 factorial, 3. All right, okay, well, anything in this column onwards is going to be a multiple of 3 because these are all factorials. So, right, okay, any number which is, well, it's got something, so yeah, we want to say of 3 digits or more and ending in 0, 0 is a multiple of 3. So that's something, because we know all of these things have got factors of 3 in. So how else are we going to get things? Well, if it ended in 3 as well. Okay, yeah, actually, or 1, 1 is going to be a multiple of 3 as well. It can't end in 1, 0, 1, because you'd have a multiple of 3 plus 1. So all of this bit that's a multiple of 3. So we need this bit to be a multiple of 3. So i.e. the last 2 digits have to be a multiple of 3 in flexadecimal, of course. In flexadecimal. So yeah, so it's got to end in 0, 0 or 1, 1. So yeah, ends in 0, 0 or 1, 1. Right, okay, that dropped out a little bit easier than I thought it was going to be. Then we got the last bit then. So if the, what's that, 1 600,000 in flexadecimal arrangements of the letters A, B, C, D, E, F are listed in alphabetical order and numbered, okay, 0, yeah, in alphabetical order. What arrangement appears in position of that? Wow, okay. So that 100000, so that's 6 digits. Arrangements of the letters A, B, C, D, E, F. Oh, that's interesting. Yeah, I'd not clocked that until now. So yeah, because these are all factorials, they are giving us the number of permutations of these things. So yeah, every time we add on a new column, we've got a new thing that we can vary around, and we're multiplying up by that number of permutations. Right, okay. Right, that's interesting, and that should certainly make this part of the question a lot easier then. So we're blocking these things out. So we're saying for each number in this column 6 here, we can go from 0 up to 5. And each one of those numbers is going to match up with a letter. So if we're at 34101, no, actually, because that last one is the very last permutation, is it? Is that how it's going to work? Or are we going to be, yeah, what is that last? So that's 6th column. So we're saying we've got, so 6 factorial, that was a 720. So we've got 6 times 120. We've got 6 blocks of 120, one for each letter. So the first 120 are going to be in, yeah, so this is, right, okay, this is counting from, oh no, it is counting from 0 is all of them in order. So counting from 0 in order, then if we've gone up to 100000, then that has done the whole lot counting from 1, not from 0. Right, so they're slightly out of step. Yeah, this is, so the thing that's slightly thrown me is this has got 6 digits, this one's got 5 digits. I'm trying to work out the implication of it beginning with a 3. And if we had counted up the number of arrangements from 0, then this number here would have been 5, 4, 3, 2, 1. As in, this 5 in the 5th column is going to go from 0 up to 5. You know, you can have one more digit than the column number. You can have a 0 or 1 in the first column. We've got 2 possible digits in column 1. So in column 5, we've got 6 possible digits, each corresponding to the 6 letters. Yeah, so that was just the thing I was trying to figure out in my mind. So that means that if we've already counted, well, we've counted up to 3. We're on our 3rd. No, that won't be our 3rd digit. That'll be our 4th digit because we're counting from 0. So all the A's would start with 0. All the B's would start with 1. The C's would start with 2. And the D's are going to start with 3. So 34101, that is then going to be D. It's our 4th one. So D is gone. We've now got the final letter from a 4 here. So that's going to be an F. And then we've got the second letter, which would be a B. Then we've got the first letter, which will be an A. And then we've got the second letter, which will be, what's left? C and E. So the second one will be E. And then we're left with a C. So that's what we're going to end up with. Right, yeah, I hadn't spotted that was what they were doing with flexadecimal until right at the end. But as soon as you got this match up here, they're talking about arrangements. You think, yeah, why is it coming out as such a nice, neat number there? Here, this 100000 for 6 letters, we've got that exact nice neat number, and yeah, it's falling out of those factorials. Of course, it's all permutations, isn't it, if we're using those factorials? Yeah, that was a very interesting question. I like that. It wasn't easy. I mean, I would imagine if you've never worked very much in binary or hexadecimal or anything like that, you'll probably find this one really difficult. But because binary is used so much, particularly if you get a career in computing or something like that, then it's relatively easy to go through something like this if you've done something similar before, because part 1 is exactly the same. Part 2 is pretty much the same once you've worked out what each column is worth, but it's the same thing really. So that's nothing new. That would be nothing new. This is the one that's slightly different with adding them up, because we had to remove a different amount in each column, because we've got a different number of digits that are allowable in each column. So that part 4 was the one that was different. Part 5 is pretty much the same, and part 6 was, yeah, interesting, but they led us to it by mentioning those arrangements. So if you've done binary, you'll fly through this probably. If you haven't, you might have found it quite difficult, but a very interesting and very useful question from that point of view.